And take it away, Mark.
That was my Jimi Hendrix imitation. Whoa. Okay, I think I'm all set. I'm going to talk to you briefly today about discoveries from Lunar Reconnaissance Orbiter and how this fits into future exploration of the moon and beyond. So the key point here is things that I think, and many other people think, we must do to prepare for future human exploration and utilization of the moon. Okay, basically over what is the rationale behind my arguments and the need. So essentially the future of the human race lies beyond the Earth-Moon system. The first step in extending our current naive knowledge and capabilities in our transition to spacefaring species requires lunar exploration. And I argue strongly that the moon is in the critical path for Mars and beyond, whatever we end up doing outside of cislunar space. So from all these great ideas that have been bounced around, not only this week, the last year, last 10 years, last 40 years in terms of lunar exploration, from that body of knowledge, we must discover sustainable architecture for lunar exploration so we can move forward. And I was in much agreement with what Paul Sputis said, in a manner that is sustainable throughout the rest of human history. We need a series of what I like to call blue-collar landers, rovers, and sample return vehicles to investigate key resource, engineering, and science questions to prepare for and support our return to the moon. The time to start is right now. Let's stop studying things, because we know a lot. And a lot of what we know is what we don't know. So we need to stop studying and start building and moving on towards the moon. Okay, there's a lot of science and engineering and resource discoveries that have come out of the LRO mission. Here's a short list. I can't even go over all of this list in the talk today, but I just threw it up here in terms of the science discovery and how we can address follow-up questions that these discoveries have raised. Of course, whenever you make one discovery, answer one question, 10 more questions come up. Like, for instance, the shrinking planet, which comes out of our discovery of the large population of low-bait scarps spread over the whole surface of the moon. A lander could investigate that to brought down a seismometer and see what kind of activity is going on today. Could also be a rover that dragged along behind it a microwave sounder to look at the fault scarp dips, so on and so forth. Pits, I'll talk a little bit about that in the talk further on. This is really, at first, an exploration target. It may become a science target. It's perfectly addressable with lander, rover, or even flying robots. And there's a poster about that if you're interested. So I'll argue that LRO is really doing what it was designed to do, and that is to pave the way for human exploration of the moon. Okay, volatiles at the poles. I put this slide together, and again, I'm not going to go through in detail all of these discoveries because we've had quite a few talks about what's been seen at the poles already this week, and I think there's one more in the session this morning. But it's really a fantastic part of science, as I mentioned before, is you discover one thing, yet you bring up more questions. And as we start seeing evidences for volatiles in, say, for instance, Shackleton, in one instrument you don't see it in another. The same thing is true for Howarth and Faustini. So it's really quite mysterious. One conclusion you could make is, well, there's something wrong with the instrumentation, and these are just bad measurements. But that's not the case. What's going on here is there's very complex processes that are sequestering volatiles in different manners, and that different instruments see to different depths within the regolith. And we don't really understand what's going on. But what we do know is there are volatiles there, and they're very important for future exploration as well as science. So really, to get down to what's going on in the polar regions of volatiles, it requires surface measurements. The lunar poles are, as I said, they're tantalizing, and yet they're vexing. We really need to get some clarity on the composition, grade, and extent of these volatiles. And this is going to require Tony talked about that in detail in an earlier talk today. Some sort of mobility on the surface or multiple mobile measurements. So robotic landers are a great idea. And they can probe in the top few meters, return definitive measurements of all the key species. Another question, that is really quite fascinating, and Nancy Chabot brought this to our attention yesterday or Monday, is the question of why do the Mercurian PSRs and the volatiles sequestered there look so different than that on the moon? The only way we're going to figure this out is to go land and get dirty in the regolith on the moon. Okay, solar system chronology. This is a big picture question. What happened when during the early solar system all the way up to today? The moon has always been the cornerstone of unraveling the solar system chronology. And already from LRO data, perhaps one major paradigm has been overturned. And that's really what are the relative ages and absolute ages of the large basins. And there's a really excellent paper by Spudis et al. I'm not saying it's excellent because I co-author. I didn't really contribute much to it, but it was Don Wilhelms and Paul Spudis. And they're really bringing the question, are we interpreting the ages of the return samples correctly? Did we only sample Imbrium in the impact melts that we're using to age date other basins on the moon? So that's a very complex question, and that requires a complex mission or series of missions. Robotic rovers to go and collect samples over broad areas that will really help us focus down where we're going to send humans to address this question. It's really a fundamental question for the whole solar system. What is the chronology of these large basin forming events early in the solar system history? Did that cataclysm actually really even happen? Okay, step to volcanism. Volcanism over time. What are the volumes of volcanic materials deposited? What are the mechanisms? What are the different compositions? Now we're seeing more and more important of unusual compositions on the moon, which are these silicic domes. And this all ties into the thermal history of the moon. Have we seen the end of lunar volcanism? Or is there a possibility of lunar volcanism in the near future? Okay, what are the age of young impacts in the inner solar system? Well, this chronology is not really well known because we don't really have robust sample collection from the youngest materials on the moon. Therefore, we can't really calibrate put the absolute calibration on the crater size frequency distributions. Now let's talk about young volcanism on the moon. One of the discoveries from LROC are these what we've nicknamed IMPs, which are irregular Mare patches, which are materials that are clearly basaltic in origin, but typically very small, and they have very, very few superposed craters on them. And when you just take for granted the crater size frequency distribution calibration, all of these materials are less than 200 million years old, possibly as young as 100 or 50 million years old. So this is really a paradigm overturn that 50 million years is not that old in geologic terms, so that means the moon is still volcanically active. Okay, we could land on one of those deposits, scoop up a sample and bring it back and answer that question. Okay, lunar pits have gotten a lot of attention. There was a talk on Monday that gave you some of the background. This is a really fantastic target for exploration. If you could utilize these sublunarian voids, you could just bring a inflatable shelter, and presto, in no time at all, you have a habitat that protects astronauts from radiation, micrometeor bombardment, and it's thermally stable, which saves a lot on power. Okay, again, young materials on the moon, Copernican impacts. We don't know the age of these very large features. This is Giordano Bruno, which is 20 kilometers in diameter. Strictly interpreting the crater size frequency distributions, this impact happened about 10 million years ago, although work by Jeff Plesha and other groups have brought into question that maybe are probably most of the impact craters we see superposed are auto-secondaries. So is this crater really 10 million years old, 1 million years old, or 1,000 years old? That's the kind of uncertainties we're talking about with Copernican materials on the moon. If you could set down on an impact melt deposit, scoop up some material, bring that back on 4 or 5 of these craters, then we could get a really good absolute calibration on the crater size circular distributions for young deposits on the moon. And then temporal imaging, this is very exciting. We've been in orbit long enough now that we're able to rephotograph areas that we photographed earlier in the mission, and now we're finding lots of new impact craters forming, and this help inform us to the hazards that are on the surface and how to engineer to have long-lived assets on the surface of the moon. Okay, now this brings us to the last slide. I know Clive was getting a little bit nervous, so I'm just about done. I think we really need a coherent and sustainable exploration strategy, and this includes polar landers with mobility to investigate the distribution of volatiles, simple yet capable long-lived rovers to measure, sample, and scout major geologic terrains, or to tie the remote sensing to the ground, allow us to assess resources. And these type of missions feed into the decision process for human targets, deliver samples from afar to human outposts, and ring out engineering, which is an incredibly important aspect for future space exploration. The robotic sample return missions to answer key science questions and assess the potential of large-scale pyroclastic deposits, so on and so forth. You know, what is the grade? What is the tonnage? It's very engineering-oriented. We need a long-range, executable, and sustainable plan for human and robotic exploration that is robust to political winds. And Paul Sputis covered that really well in his talk, I think. So with that, I will finish, and thank you very much for listening.
Time for a quick question. Wow.
That's so hurtful.
It is. It's a little insulting, isn't it?
Yes, it is.
Madhu Thangavelu from University of Southern California. Mark, I'm delighted to see all that. And my question is, what do you mean by the term long-range planning? Can you give us some idea, maybe Clive too? How long? And Paul is in the group?
Yeah, I think that's an easy question to answer. We don't really seem to do long-range planning in space exploration, right? We do these one-off missions we get all excited about, go spend a lot of money, and then it's done, and then we all scramble and we go try to do something else. What we need to do by a long-range plan is, okay, we're going to investigate the moon as a planet in a holistical way, and this requires all sorts of different geological and geophysical measurements. From that, then you will start learning about resources, you'll start learning about science, you know, rather than focusing on one very specific question. So we have to face the reality that to explore the moon as a planet is going to require 10 or 20 or 30 missions. You have to make them, you know, sustainable, cheap, and that's why I like to use the word, they're kind of like blue-collar missions. You have to go out there, dig holes, and take measurements, and do this repeatedly. It's a lot of hard work over, you know, a long time span, as opposed to this model where we make one great big spacecraft that costs $1 billion, and we go land it, and we do this one thing, and then we're exhausted, you know, fiscally for the next 20 years, and it's not sustained, and there's no long-range benefit from it.
Multi-decadal. Thanks. I think it's quick follow-up, very quick, and a short answer, please.
I'm not capable of giving short answers.
So, Victoria Friedenson, headquarters. So in light of that approach, do you see it as being a outgrowth of the decadal survey, different from the decadal survey, or let's toss it and do a definitive long-range strategy, said the heretic from human exploration?
I don't think the decadal study is really all that relevant, to tell you the truth, to the moon.
Said the heretic from ASU.
And the decadal study is almost stale the day it comes out, because science is so, you know, it progresses so rapidly, you know. But I know it's an important document for NASA, but this is something different. We're talking about, you know, engineering, we're talking about resources, talking about discovering, you know, the planet, the geology and geophysics of the planet in a holistic manner. Right? That's not what the decadal study is about.
All right, thank you, Mark. Let's